To make this a little easier on myself, I'm going to multiply these two so we can kind of condense them into one number. So 100.0 grams times 4.184 joules per gram degrees Celsius. Our grams units here are going to cancel with the per grams here. So those are going away. So what's going to be left is just units of joules per degree Celsius. Okay, 100 times 4.184 should be 418.4. I'm going to double check in my calculator just to make sure my mental math is on the right track. Yes, okay. Alright, so I've condensed the mass and the specific heat capacity by multiplying those together, but it's still multiplied to my change in temperature here. Okay. I also still have this heat value over here on the left side from all that heat my water is supposedly absorbing. Tidy that up a little bit. There we go. Okay, so now if I want to solve for this change in temperature, I'm going to have to get it alone by getting rid of this guy here. If they're being multiplied right now, I can get rid of it by doing the opposite. I can divide by this. So that's what I'm going to do. I'm going to divide both sides by this 418.4, or if you want, you can do a little shortcut where you divide this over to the other side. So you can kind of just like get rid of that, divide it here. I'm going to show it the long way. Okay, so our 418.4 joules per degree Celsius is going to cancel out totally on the right side. So all we have left is this delta T. Okay, on the left side, I'm going to get a new number from this when I divide this out. All right, and I will also get a new unit. Let's stick with the dark green. Okay, so I'm going to take 20,169.144 divided by 418.4. All right, and I get 48.21-ish. All right, and this should be equal to my change in temperature, delta T. Okay, so if you get this far and you're like, I haven't been keeping track of the units, we know that a change in temperature is supposed to be in degrees Celsius. So we could just kind of cheat it and say, degrees Celsius and put that there. Okay, or we can double check and make sure the units cancel correctly. So joules divided by joules cancels out. Those are gone. What we're left with is degrees Celsius, but it's kind of being divided after it's being divided. That flips it. It undoes it. So this goes to the top instead of being on the bottom of the bottom, if that makes sense. It's like dividing by a fraction, like 1/2. Okay? Whatever's on the bottom of that fraction flips to the top. You can try it in your calculator. Take 1 divided by 1/2, you'll get 2. If you take 1 divided by 1/3, you get 3. 1 divided by 1/4 gets you 4, on and on and on. Okay, so by dividing by our per degree Celsius, flips up to the top, so our unit is going to be in degrees Celsius. Okay, so based on our calculations, our water should have gotten 48.21 degrees Celsius hotter. than it was before. Now, this isn't actually the end of the problem. We have one more thing to do, and that's to figure out what the new temperature of the water is going to be after it raises by this much. Okay, if we check back in our data, our water started out about 22 degrees Celsius. If it goes up by 48.21 degrees Celsius, the final temperature of the water is going to be 48.21 degrees Celsius higher than it used to be. So 22 plus 48.21 is going to be, let's see, 20 and 40 would be 60, 2 and 8 would be another 10, so that's 70.21, about 70.21 degrees Celsius. Okay, and just to make sure I'm not messing that up, 22 plus 48.21, yes. Okay, looks good to me. Okay, so this is our final temperature. Okay, whenever we calculate a delta T, that means nothing about the temperature that we start with and the temperature that we end with. All it tells us is how that starting temperature increases or decreases from there. Since we're absorbing heat, that means our temperature should go up. Our temperature change is positive, so we apply a positive temperature change to our starting temperature to bump it up. If we were looking at how the temperature of the nickel changed as we put it in the water, it would cool down. It loses that heat as it gives it away to the water, and so its temperature change would be negative. So you'd apply a negative temperature change to that really, really hot temperature and have it drop all the way down to something a lot cooler.